right, so today is, again, it's just continuing to get better at sum of forces. We're going to look at a couple separate problems that present kind of their own unique challenges when it comes to problems that you're going to see kind of as you prepare for this, and also kind of just kind of a continuation of a technique that I keep pushing, keep pushing, keep pushing. But yeah, that's what we're going to work on first. So for the sake of the video, I'm going to draw a picture of what we're going to do over here. But as you see over here on the right, I'm straight up actually going to do it. So all we're going to do right now is we're going to take a coffee cup, okay, and we are going to slide it across. It's a wooden board on the table. Now I've already measured a couple things about this coffee cup, but you're going to be surprised, I think, at like what I give you here, okay, or actually let's just say the lack of what I give you here. Okay, so I have measured already that the mu k between the coffee cup and the wooden board, I showed you yesterday how to measure mu k, is 0.2. 0.2. 20% of force normal becomes force friction. The only other measurement I'm actually going to take from just straight up doing something with it. There's only one other measurement that we're going to take, and that's this. We've got a coffee cup. I'm going to start it right here. I'm going to slide the coffee cup across the table, attempting really hard not to take this awesome Batman gigantic coffee mug and accidentally slide it off the table. If it does, we'll turn it into a different problem. All right, so here we go. Okay, it slid from here to about there, so I'm going to say 60 centimeters. Would be what? Right, I'm sorry, what measurement would that be that would help us? Displace. So 0.6 meters if you prefer. Very good. Question. How fast did I throw it? Now, as you look at this problem, the first thing that you're going to probably remark on, and similar problems to it, is there's not enough information. When there's not enough information in a problem, or it seems like there's not enough information, what you want to do is still go through the exact same steps. All right. Now, there is actually one more piece of information that you witnessed just now that you actually can put down up here as well. What is it? Discuss quickly in your group. Think of the situation. Okay. Think of all the variables that we've discussed thus far this year. What other variables would you technically know? In this case, would I slid this across the table? Okay. And asking the question, how fast? I said VI here. Basically, the question when this would, how fast did Spainhour throw the mug? How fast was it going when it left his hand? Discuss. Anybody got it? I don't know if I can do it exactly 60 centimeters again, but I'll demonstrate again, because technically 60 centimeters resulted from the exact VI that I threw, so if I don't throw exactly that same VI, it's probably not going to be pretty close, actually. It's not that there it was. So now, what's the other variable you know here? Velocity find, correct. What's velocity find? Zero. Now, a couple points of interest here. You see that I'm asking for a kinematic variable. And how many kinematic variables do we have in this problem? 2. How many do we need to do just basic kinematics? 3. So, we don't have enough information, kinematically speaking, in order to currently solve this problem. But, given the stuff from this chapter, what kinematic variable can we go find? We can always go find acceleration, right? Acceleration is a kinematic variable. So if I want to go get the acceleration on the cup, what do I need to do? I need to sum the forces. And to sum the forces, what should I probably do first? Force diagram. So do the force diagram. Now, a point of interest here, because there's a couple things that happened up there. There's technically 2 different force diagrams that you can look at. There's one when I was throwing it, and there's another when it was sliding. Which one should you use and why? What's that? No. Why when I was sliding? Should that be the variable that you look at? because we have these two variables here that correspond to that section of time, right? So we need the acceleration that corresponds to that section of time. So you need to do the force diagram on that mug when it is sliding. So do that real quick. I originally thought of doing this mug right here. The problem is I have coffee in this mug, and then I want to keep drinking the coffee in this mug, which technically changes some of the results. It doesn't. All right, what's the force diagram?
Force gravity down. Force normal up.
Mm-hmm.
Force friction back.
Yeah, I'm going to say this is going to the right on my picture. That works out for you. It doesn't for me, but it does for you. Okay. Force gravity down, force normal up, and force friction back. Now, there's not enough information here, and there's a certain thing here, but let's point out, let's kind of put this to the type of problem I'm trying to show right now. Just put the nail on the head and say, what is the piece of information that you look up here and is probably the most remarkable that is missing, that you feel like probably should be given to you? Mass. Why is there no mass up here? Okay, so if you want even to put like a label on this problem so you can kind of recognize it for the future, we'll call this no mass problem. Or actually, no mass, no problem. I see that. It's not funny. All right, so how do we attack a problem when there's no mass? Well, attack it the same way as you always do. Okay. What would you do right now if you were going to go find acceleration?
Some forces in y.
You started with the x and you said y. Let's discuss that real quick because that's an important point of interest. Why did you start with x?
Because it's like a tendency to do it because it's moving in the x.
Right, it's accelerating in the x. We will inevitably have to do the x. That's where the acceleration is. Why do you have to sum the forces in the y?
Because you need to find force normal.
Force normal. Now, I also highlight that because there will be problems on both your homework as well as potentially on the test that try to make things easier by saying, let's go ahead and make this 0, or talk about a frictionless surface. If it talks about a friction, now this would be a dumb problem to have a frictionless surface, but if they do, please keep in mind that obviously you don't need to sum forces in the y. Now, if this was a frictionless surface, again, this would be a dumb example, because what would this mug do if it were frictionless? After throwing, it would go that way forever, so it would definitely not stop at any point in time. This doesn't match in that case. But yeah, let's go ahead and sum the forces in the y. Go ahead and do that. As a matter of fact, go ahead and sum the forces in the x, just like we always do. And do the sum forces in the y. Does it accelerate? Sum of forces in the x. Does it accelerate? I'll give you a minute to get out in front of me. All right, what are the sum of forces in the y?
Plus Fn minus Fg.
Plus Fn minus Fg. Is it accelerating in the y? No. That's 0. This is 0. Force normal equals force gravity. Okay. What are the sum of forces in the x? Okay. And is it accelerating? Yes. And how would you usually, again, this is a spot where people get stuck because they would go, yeah, but to get force gravity, what do you need? Mass. So they would just stop and they go, well, I need mass. I don't have mass. I'm going to stop. Here's what I want you to do. Don't stop. Okay? Do the problem as though you had mass. Okay? Meaning we would calculate mg. Yes? Now, we don't have that. Don't worry about it. Let's continue on as though mg represents force friction. Sorry, force normal, because it does. What would you do right now if you had a number for force normal? Correct. You would use the equation, force friction equals mu times force normal. Yes? And force normal is equal to this right here. So you would say force friction is equal to mu times m times g. Yes.
Wait, what did we just do?
We said force normal is equal to mg. Yes. Our equation here, force friction is equal to mu times force normal. Since force normal is equal to mg. I just wrote this again, but instead of force normal, I wrote mg instead. So if you want here, I'll put the parentheses around this. This is just mu times force normal. Okay? Now, again, we can't get a number yet. But what would you do with that equation, with that number, if you had it right now? You knew force friction. Like I said, force friction is 10. You have a number. What would you do with that number right now? You'd plug it up into sum of forces in the x, right? So instead of taking the number and doing that, we're just going to do that exact same thing with the equation, right? So right here, instead of minus force friction, I have minus mu times m times g. And right here is the reason you don't need mass. I can explain this in two ways, but let's start with the easier one that you should notice. Mathematically, why do you not need mass? They cancel. Yeah, divide mass on both sides, they're going to cancel. So right here, we get that acceleration is equal to negative mu times g. Do we know mu? Do we know g? The rest of this problem is relatively easy. So I'm going to take a little bit extra time once again to highlight this in a problem. Okay? Why does this work? Well, let's say we had a mass and we could calculate force of gravity. As a matter of fact, I have actually calculated the force of gravity on this. It's 7.6 newtons. Okay, 7.6 newtons. Working my way back. Actually, I didn't do this part yet. 7.6 divided by 9.8. This thing has a mass 776 grams, or 0.776 kilograms. Now let's say I go to the back and I put more water in it. Okay, so it's got more and more and more mass. Enough water that I double the mass of that particular cup. If we look at that, what would change up here if I doubled the mass of the cup? Well, let's start off with the basic one. First thing that would double is force of gravity. But that would pull the thing down further into the ground. Yes? Which would mean more double the force normal, right? Because force normal and force friction are proportional, double the force normal means double the friction. Now, if I just stopped there and I said double the force, what effect would that have on acceleration? You should appropriately say, well, double the force means double the acceleration, right? Except, if you come over here in Newton's second law, there are two things that mass affects. The first one in this case, this would be doubled. It'd have twice as much force on it. But what does twice the mass also mean? It also has twice as much inertia. This is the representation of inertia. So is there twice as much force on it? Yeah. Is it twice as hard to stop? Yeah. So would we get the exact same effect either way? Yes. It doesn't actually matter how much mass is in there as far as acceleration of friction is concerned, because twice the mass means twice the gravity, means twice the normal, means twice the friction, twice the force, but also twice the inertia. In other words, if this goes up by 2 and that also goes up by 2, what effect is there on acceleration? Absolutely none. And thus the mass doesn't matter. And again, if you struggled with that conceptually, you can see it mathematically right here. Mathematically, it shows the same thing that the concepts do, that the mass doesn't matter. So if we continue from here, we'll go ahead and plug numbers in now. Acceleration is equal to negative 0.2 times g, which would end up at negative 1.96 meters per second squared. And now, do you have 3 kinematic variables? Yeah, so now it's trying to figure out which problem that is. Which problem is that? That would be, yes, that is the right one, correct. So we'll just go over here. I'll erase this part. Velocity final squared equals velocity initial squared. Is this one-dimensional or two-dimensional? One, it's just going in a straight line, so we're just 3 variables, plug and chug. Don't plug variables in unless it's a 0. That's a 0. I'm going to subtract that term on both sides. I don't like it when I do that. Those look like 2's. And then I'm going to square root both sides to get rid of that, which looks bad because there's a negative under a square root, but what saves us is the negative on the acceleration, so we plug this in. Negative 2 times negative 1.96 meters per second squared times 0.6 meters. I square root the whole thing, and I find out that Spainhour threw this at 2 times 1.96 is roughly 4 times 0.6 would be 2.4. Square root it, you're going to end up with probably 1.4-ish. I was wrong. Is that exactly right, 1.5?
1.53362.
Let's go 1.53. Remember, my strong suggestion to you guys is just get used to using 3 sig figs. That's a standard method through most of science, even if you're not tracking anything in the rest of the problem. Okay, so there's 2 things to highlight here. Hopefully you were okay on both of them. The first thing is, what do I do if there's no mass? Hopefully you are already, I said this many a time, okay, and let's continue on with here. Physics is done best when you don't plug numbers in as long as possible. As a matter of fact, if you did this problem again with numbers, like if I gave you the mass and you tried to do it as fast as we could, you can't. You really can't do it as fast. And the reason is why is because when you got here, you'd have to rewrite and write all the numbers, and then you'd have to get out your calculator and do that, and then you'd have to write this equation, plug in the numbers, and then you'd have to plug all that in, and then you'd have to come over here and plug in the numbers, and blah, blah, blah. But you have to take like 4 breaks to plug numbers in and to calculate, as opposed to, I can pretty much do this entire problem without any sort of calculator whatsoever till the very end. I only plug numbers in right here because you guys are uncomfortable not plugging numbers in. As a matter of fact, if this is me doing the problem, instead of plugging numbers in, I know acceleration is equal to negative mu times g. So right here, instead of doing this, I would say this is equal to, sorry, I'll go down here because I'm running out of space here. Negative 2 times negative mu times g times delta x square root equals vi. And that's the first time I'd actually have to plug numbers into that particular problem. And I'd also get my 1.53 a little bit quickly at the end there. So don't stop using numbers. Start using those variables. Get better at it. Push yourself to do it, okay? It makes life easier, more accurate, and you can see concepts a little bit later on. Questions or concerns on any of these? Let's move on to the second problem of the day. So we're going to take that same coffee mug and that same board. This time I'm going to turn the board and hopefully, again, not break the coffee mug. And we're going to set up almost the exact situation that we had in the lab, minus one major difference. The major difference in this particular case is we do have the presence of friction. Now, in this particular case, I am going to tell you some masses, okay? Like I said a second ago. Oops, it is. Oh, shoot, I always have to redo this. I have to think about how to go up here. All right. And then you go through, and you do that. Yep, okay, sorry. Fair enough. Okay, so exact setup, the exact same setup as the lab, okay? But there's the presence of friction. The other thing we're going to do in this case is in the lab, I told you to make an assumption that is not true. And it was pretty true in the lab. It's definitely not true here, okay? And that is that that gravity down and tension up would be equal. Please draw the force diagram on both of those objects. You can see, hopefully, by the way, that this thing is accelerating, okay? And I'll tell you that this is, as we said before, 776 grams. That down there that's pulling is 200 grams. I'll write this on the board too for anybody watching this later in just a second. And we measured last time the mu value between these two surfaces is already 0.2. The question in play is, what is the acceleration of the mug? That's it. what should the acceleration be of this particular mug? So here's the setup. We have an object right here. This is the coffee mug, okay? And the coffee mug is being pulled across a pulley, like I said, extraordinarily similar to the lab that we did, by a mass pulling straight down. This coffee mug has a mass of 776 grams. This mass that's hanging right here, I'll call that mass hanging, is 200 grams. The coefficient of friction up here is 0.2, and the question is, what's the acceleration? This is a problem in which you have two objects. Okay? We've got two objects that we are dealing with here. Since we have two objects, each object requires its own individual force diagram. Let's begin with the top one here. By the way, if you feel like you're completely fine on this, just get going without us. All right, what's the force diagram on the top one? Force gravity down. Now, a very important thing here before we get too far, and that is, there are two force gravities in this problem. As such, make sure that you use subscripts to do not confuse yourself. Now, if you want to be as simple as saying 1 and 2, that's completely fine. If you want to be more descriptive, that's fine. Use subscripts that work for you. I don't need to know what the subscripts are, but they should be logical. For me, in this case, I'm going to say cup and I'm going to say hanging. But if you wanted to use 1 and 2 or A and B or whatever you wanted, that's fine. So in other words, I'm not just going to write force of gravity. I'm going to write this is the force gravity of the cup. Okay, next. Force normal up. Very good. Next. Force tension to the right. And should friction be equal, less, or greater than tension? Why? Accelerating to the right. Yes?
Is that mass 776?
Yes. Okay, now the mass hanging. What do you got?
Force tension up.
Force tension up. And
Force gravity.
should force gravity be equal, greater, or less than force tension? Greater. How come? What's that?
It's like going down, the tension's not enough.
That's not quite right. Because if this is going down in a certain pace, these are equal. How do you know this one's bigger? It's accelerating down. Okay? If this is going down at a constant velocity, then these two are in fact equal. It's following first law. The fact that it's accelerating is why these two are different. And, as I said before, if this is force gravity of cup, this over here is force gravity hanging. Now you'll notice, by the way, that mine is definitely not to scale. This is not on purpose. This should definitely be, if you look at the ratios here, this should roughly be a little bit less than a fourth, or sorry, a little bit more than a fourth of this line right here because of the size of their mass. I'm not worried about that. I'm only going to be worried in a force diagram about the relative sizes. Yes?
Why would there be no force friction?
What's that?
Why would there be no force friction for the...
Excellent question. We are going to, there's going to be friction, there is going to be a little bit of air friction. But again, we're going back in our problems to kind of ignoring air friction. And the reason why that is very reasonable is because this was not moving fast enough. Like, if you were that mass, would you expect a significant wind, a significant push that would affect our results in this case? No. So you are right that there's friction. It is so ridiculously minuscule that we can assume it is zero. And for all of your problems, you can go ahead and say that air friction is going to be somewhat ignored. Okay? Technically, if you wanted to put air friction, we should actually make this surface friction and put another air friction up here as well. But again, it's going to be minuscule. How we doing? All right, let's move on. The biggest thing with this to understand, and if you get this, I think the rest of this will fall into place, is number one, are both of these going to accelerate? Yes. Are both of them going to accelerate to the exact same amount? Yes. Think about this. Are they both going to start at the same velocity? Yes. Are they both going to cover the same magnitude of displacement? Yes. Are they both going to take the same amount of time to do it? So those are three kinematic variables that are all the same. Or another way to put this is, are they both going to be going the same velocity at the very end? Yeah, they're both going to be going the same speed, which means they do have the same acceleration. That's an important thing. Now, if I just rely on my standard way of setting up x and y, this acceleration will be in the positive x direction. Yes? This one's going to be in the negative y direction. To make math easier, we remember that we set up the x and y. We decide what the x and y is. Yes? So here's the standard way of doing it. Whichever way the object is moving, what you do is you define that way as positive. Now, you'll notice up here, this changes absolutely nothing. Okay? And when I say this way, that's the y for this guy. We don't really need to mess around with the y over here at all. Once we have this set up, the force diagrams, we've set up the positive. That positive is going to be very helpful for this. Let's go ahead and start doing these problems. Okay? So, how am I going to find the ultimate find is find the acceleration, which is, of course, like we said, the same on both. So, what do you want me to do first?
Sum of forces.
I like it. Which one and where?
Both.
Agreed. Where do you want me to start?
The top one on the y.
Start with the top one on the y. So we are summing the forces, and you know what? It's probably not a bad idea. You don't have to do this. I'm not requiring it, but organization helps you long term. Let's just go ahead and say cup up here. It's not a bad idea to put a label on this just so I don't accidentally mix them up later. So sum of the forces in the y equals mass times acceleration in the y. What are the sum of forces in the y for the cup? Yeah, the same old thing, same old is accelerating. In the y? No. Okay, so this is equal to 0. So we get what we expect, force normal is equal to force gravity. Okay, and how do we calculate force gravity?
Would force gravity be positive since down is positive?
Excellent question. What I said earlier, though, is that positive being down is only really for the acceleration side of things. You don't have to mess around. Why did you do that? What did you do? What are you doing now? What? Changing my... All right. Okay, you don't have to do that. If you want to, it's fine. It's going to say the same thing, right? If you look up there, you're going to see negative force normal, positive force gravity. You're going to get the exact same conversation. It's not going to hurt anything. But you really only have to switch the direction in the direction the object is moving, which is the x for here and the y over here. Okay? All right. So how do we calculate force gravity? mg. This is that time where I start to be like, hey, you could, if you want, plug the numbers in. I don't want to. I really don't want to. I'm not gonna. So what would I do with mg? What would I do with force normal? Well, we got that. Yeah, we got that here. I mean, I have this in a line, so I'm not going to rewrite anything. But yes, that is true. So what do you want to do with force normal now? Why did we go get force normal? Go get force friction. Force friction is equal to mu times m times g. Actually, I should always write the equation first. All right. Now we have friction. What do you want to do? And again, if you want to plug the numbers in, feel free. What do you want to do now? I like it. What are the sum of forces in the x? Force tension minus force friction equals mass times acceleration. This is my force friction, so I'm going to plug it up here. So we have force tension minus mu mg equals ma. Notice I dropped the x because this is just the total acceleration over here. Now, cool, easy peasy. Seems like a problem that we've done 1,000 times until you pay attention to this particular fact. Do you know mass? Actually, I don't know why I started over on that side. Do we know tension? No. Do we know mu? Do we know m? Do we know g? Do we know m? Okay. So, oh, sorry. Do we know a? We got two unknowns, people. We don't know tension. We don't know acceleration. If only we had some methodology of solving when we have two unknowns. What do we need to do if we have two unknowns? Another equation with the same two unknowns. Where am I possibly going to go to get another equation with the same two unknowns? The hanging mass, yes. Let's go ahead and go down here. All right. What do you want me to do with the hanging mass? Sum of the forces in the y? I like it. Now, ooh, I made a mistake. I just, by omission. You will mess this up unless you do this, which I screwed up immediately. If you're dealing with two objects, and I was mentioning this earlier and then totally forgot here, you better be careful because this mass needs to be a very particular mass. If you don't make it into a number, you better say what mass that is. What mass is this that gave us friction up here, that gave us force normal over here? That would be the cup, correct. And whose mass is this? What object is accelerating in these diagrams, in these sum of forces? The cup. So this is the cup's inertia in this case. So that can't be just a generic m. It better be the mass of the cup. All right. I say that because I come down here, and now we talk about the hanging mass. All right. So sum of forces equals mass times acceleration in the y. But now what's doing the accelerating? Hanging mass. All right. So what are the sum of forces?
Force tension minus force gravity.
It would usually be.
Oh.
It would usually be that, but since we switched it, it should be
Force gravity minus force tension.
correct.
Is it ickier if you do it the like regular,
Do what now?
like not switching around how you're like?
It is not easier. I'll tell you. Oh, sorry. Go ahead.
I was just wondering if it's like way ickier or like.
Not way. Not way ickier. I'll just tell you what you have to do in that case is you have to recognize that the acceleration is negative in this case. So what you do is you just put a negative out in front of this to cancel the negative that's inside. I think it's less methodical. I think it's kind of more like you have to get really into the weeds to remember it is type deal. Where this, I think that you can kind of like, okay, I don't remember everything, but I know what the next step is, but I know what I do next, but I know how to, I know that I know that I know. So that's my suggestion. Okay, all right, so here, force gravity hanging. How do we calculate force gravity hanging? Mass of hanging times g. And if you look at this equation, you will notice, watch here, I know it, I know it, I don't know it, I know it, I don't know it. So I have two unknowns. Are they the same two unknowns? Yes. So at this point in time, between this guy and this guy, and let's go ahead and actually copy here. Not that you need to, but just a little bit better organizing here for me. Those are your two equations with the same two unknowns. Now, at this point in time, it's just math. We've talked about this. The physics is done. We are at math. I'm going to share with you what is definitely the easier way to do this and why it's the easier way to do this. Okay? You remember that you dealt a lot in system of equations with substitution. As a matter of fact, it's probably most of your guys' default. Go solve for one, plug it in the other. Yes? But there was a second method that you used a little bit, but almost immediately forgot because it's not usually used. What was that other method? Elimination. That is actually very helpful in this case, so I'm going to remind you of it. I'm going to remind you why it works, and I'm going to show you why when you need to pay attention to it in physics, because it makes things a little bit easier. Okay? Don't forget that this equal sign means that this is, who knows, some number over here, right? Like this is the number 10, and that's the number 10. Yes, we know that's what the equal sign essentially means. And same thing over here. Now, do these have to equal those? No. But we know that if this is 6 over here, that has to be 6 over there. Yes? Because of that general rule, what it means is I can always take the left side of this and the left side of that, add them or subtract them, and then do the same thing to the right sides, and it will still be equal. Why? Because 10 plus 6 and 10 plus 6 are both 16, and 10 minus 6 and 10 minus 6 are both still 4. Yes? So, elimination, basically I want you to see why we can add both sides, but elimination works by taking one of the two variables and essentially using this process to cancel them out. This happens a lot in physics because of Newton's third law. What is Newton's third law? For every force, there is an equal and opposite force. You'll notice here, force tension is negative. Here, force tension is positive because they're equal and opposite. And what will equal and opposites do if added together? Cancel. So if you want to use substitution, it will absolutely work here. But elimination is vastly easier because I'm just going to take the left side of this and add the left side of that. Be careful of the subscripts here. And you'll notice that force tensions cancel. Now, if that was it, honestly, I wouldn't worry too much about it. But the other nice thing, I'll just point this out to you, the other really nice thing about elimination is it also isolates the other variable at the exact same time. You'll notice, is the variable over on one side by itself? Yeah. So what would you do now? Nope, not yet. We're doing algebra to isolate first. What are we trying to get by itself? Acceleration. So what do? You have a in two terms. What should you do with it? How do you combine them? Sorry, you could do it that way. I was just looking for a simple factor, right? We factor out the a. And if we factor out the a, we get, you were already doing it, mh plus mc times a is equal to mhg minus mu mcg. And then we divide both sides by mhc. And once again, I'll point out something that I told you last time, and that is I didn't have to do any number calculations. I did not have to grab my calculator. If I know how to do this, I can go from writing from beginning to end, get this all isolated, and now I can actually go and grab my calculator. And if you want to, great. I honestly don't care if you do, because you know what we just did? We just solved this problem for every mass hanging, for every mass of cup. Because what changes now if I put a bunch of water in the cup? The masses change, but I measure them and I plug those in. This problem is now done for all possible options whatsoever. All you got to do is figure out what the starting numbers are. Yes, Christine?
That's MH at the bottom right.
It should be MHG minus mu MCG over MH. Oh my goodness, you're right. No, you're fine. Listen, my handwriting was bad to begin with. If you dealt with me mostly over on the whiteboard, you would have found that it's bad. This thing amplifies it even more. So I need to get better. I apologize. But yeah, any questions on how to do these? I'm going to put up 2 more problems tonight in video form on each of these problems. Okay, I'll tell you what they are ahead of time. Okay, just so that you can know. The first one is by the Frodo problem from yesterday. Okay, and I'm going to show you that in the Frodo problem, you also don't need to know the mass of Frodo at all. The mass of Frodo did not matter in the slightest. You can watch that video, you don't have to, but it will also correlate to some problems that are on your particular homework. Okay, the other thing I'm going to show you is kind of similar there. I'm going to show you a problem in which instead of that, basically kind of a similar setup, except we have two objects once again, but one of the two objects is going to be on an incline. So kind of a combination of that rotating axis that we dealt with yesterday, as well as two objects that I'm kind of showing you today. Those are the two videos that I'm going to create so that you can look at. I'll put a friction on this one. I will probably make this one over here frictionless also, so you can see potentially how to deal with that whole situation if you would like to watch them. Otherwise, I'm done teaching you new stuff. Actually, technically, this wasn't all new. It was just kind of a rearrangement of stuff that we already did. Are there questions? Yes.
Is this going to be on the test?
Very likely. Very likely, yes. I mean, it's just a practice of this particular stuff. So, yes, it's very possible. Other questions or concerns? I'm going to stop the video then.